talked about the meaning of this curve and some of the distinctions between steady state and microscopic rate constants. So this is the most important slide about this, right? Which this is a plot of V equals V max S divided by Km plus S. And the variables on top indicate the meaning of V for the initial velocity at very high concentrations of S or very low concentrations of S. Right? This line, this straight line here is simply meant to indicate that this is roughly linear at very low S. It doesn't mean anything that that straight line goes up through the roof there. It just indicates a straight line. All right, so you can substitute in, for example, substrate concentrations much less than Km in the equation V equals V max S divided by Km plus S, which is the Michaelis-Menten equation that we derived. And if you do that, what you get is a linear equation. Okay? And the linear equation will approximately fit this line here. And as we derived last time, that will let you calculate Kcat upon Km, although not the individual parameters Kcat and Km separately. Right? In order to measure those, you have to be measuring the substrate, you have to be measuring velocities at substrate concentrations that are somewhere around the Km. And the best thing to do when you're setting up your experiment is to measure at substrate concentrations that bracket the Km. When you start, you don't know where that is, so you do a few tests. If you measure V versus T on this plot, and you measure it at, say, 1 micromolar substrate concentration, and you get a VO from your actual data in hand, and then you double the substrate concentration and you get twice VO, and you quadruple it and you get 4 times VO. That's linear. Double, double, 4, 4. Right? So if that's the case, then where are you on this curve? Right? You're down at the very low end where it's still linear. Right? So you better go up in S. Right? You go to 4 to 8. Now instead of doubling, it goes up, but it doesn't go up as much as to double. For 8 to 16, it still goes up. But again, not as much. Until finally you go up in S high enough, 100 micromolar, 200, whatever. Now you're way up on the upper right. You can increase S all you want, and V0 will still not increase. Because now you're saturated. You've observed saturation kinetics, which is the fundamental property of enzymes. Any questions about this before we move on? Yeah.
I'm just wondering, just to confirm, so the Michaelis method is plotting is specific to one substrate, one enzyme, no allosteric regulation stuff.
That's correct. We will see later today that Michaelis-Menten kinetics does not apply to allosteric enzymes. It only applies to Michaelis-Menten enzymes. And in a couple slides, I'll give you another detail about how to do it when there's multiple substrates and it's still Michaelis-Menten enzyme. Other questions about Michaelis-Menten? Yeah, sorry.
So would that also work if you had multiple enzymes and they all just happen to be Michaelis enzymes? Would that also work for, like, let's say, for a pathway?
Yeah, there's plenty of examples of pathways where all the enzymes are Michaelis enzymes. Well, maybe I shouldn't say plenty, because the enzymes that are regulated in pathways, and you always have some regulation in cells, regulated enzymes tend to be allosteric enzymes and not behaving like Michaelis-Menten. So if you have a pathway of 10 enzymes, you might have, like glycolysis, 7 of them Michaelis-Menten and 3 of them not. Yeah. So here's chymotrypsin again. And I just want to illustrate some of the points about kinetics by reference to our favorite enzyme. So here are 3 chymotrypsin substrates, and here are some kinetic parameters on them. This is back in the chymotrypsin reading, but we didn't talk about it then because we hadn't talked about what Kcat and Km mean. Now that you know what those things mean, the slide has a little bit more meaning. So here's the Phi, right, next to the peptide bond that's cleaved. Right? And the only difference among these 3 substrates is that there's a little more cabbage out here on the end, right? That's it. So there's more to bind the enzyme. Right? There's more potential for interactions between the substrate and the enzyme in substrates B and C as compared to A. Right? So if A has kinetic parameters of 0.06 per second, 31 millimolar, and that's the ratio per molarity per second, so the units just changed there, that's why the numbers look a little funky. What happens if you add this little bit on here, right? It basically amounts to adding a glycine, right? CH2 is a glycine. Right? So you have a peptide, it's only got 2 amino acids, you cut it in half. Now you have a tripeptide with a glycine on the end of it, right? What happens? Kcat approximately doubles. Kn goes down by a factor of 2, and subject to rounding errors, Kcat upon Km goes up by a factor of 5. So it's the same enzyme, it's the same kinetics, there's no change in the catalytic triad, everything is exactly the same mechanism, and yet these parameters are different. They're not hugely different, but they're certainly different. Now we'll take this glycine and make an alanine out of it, so we'll add a single methyl group to substitute for one of those hydrogens. And now we get a 20-fold improvement in Kcat. And Km pretty much doesn't change. Goes up a little bit. These Km numbers are, you look at those, you're like, okay, not much change in Km. But Kcat, huge effect. And so therefore Kcat upon Km, huge effect. So we have this effect on efficiency. So Kcat upon Km is often used as a single number to denote the efficiency of the enzyme. The units are per mole per second. And so the efficiency of this enzyme just got better by 57-fold compared to from C to A, just by adding an alanine on the end of it. So that's a lot more efficiency, considering that it's the same enzyme doing the same reaction, right? And most of that is because the Kcat got a lot better. Okay? Another thing that happens, we don't have the data here, but if you have peptides that have non-cognate P1 residue, so P1 would be the phi residue. That's what P1 means here. Let's say you had lice instead of phi, and you got it to bind the same way, so lice was in the pocket. Right? You know that it's going to like the phi substrate more than the lice substrate. But if the substrates are bigger, it likes the phi over the lice even more than if the substrates were smaller. So the specificity of phi divided by lice is better if the substrates are bigger. So what's up with this? Distal binding interactions increase the steady state rate. So this is an example of using binding energy in catalysis. So it could show up in different kinetic parameters. It could show up in Kcat or Kn. Or if we were looking at the microscopic parameters, it could show up in K1, K2, or K3. Right? It could show up in one of these little microscopic parameters. Right? So let's say that Kcat, we know that Kcat is not necessarily any particular microscopic parameter. It's always the slowest forward step after binding. But let's say that Kcat is actually the chemistry in this case. So what is it about these distal interactions that would improve the chemistry by such a substantial amount? How would that actually work in terms of structure?
There'd be more interactions between the substrate and the enzyme, which would allow for potentially more interactions, which would allow for more free energy release, so a lower activation energy. So in a sense, isn't it like to the inverse?
Yeah, so lower activation energy, so I'll buy that. But how? How lower activation? By what mechanism would you get a lower activation energy?
Well, wouldn't it also affect with sterics? Because with having that pole now attached to it, that'll kind of force it to be in a certain
okay.
condition.
And can you say that a little bit more precisely?
It'll have greater specificity to it.
No, we're not talking about specificity now. We're just talking about the one substrate, the phi substrate, the one it likes. It's just getting a lot better in Kcat. And you're on the right track, I think. Yeah. Yes. Decrease entropy where? Yeah. Yeah, where in the active site exactly? Sorry? Not really, because we just said Kcat is Kchem, chemistry. So really, what the conventional explanation for this is you're driving a reduction in entropy. You're using the binding energy to better immobilize the scissile peptide bond with respect to CR195 and His57. If that carbonyl carbon that has to get attacked is nailed in that position that much better, exactly right, half an angstrom better position, so it could get better, or it could get more ordered, or both. Better positioning, better order, so less dynamic motions. Right, so more of the time exactly where it needs to be. Everybody see that? Right. I mean, whole books written about this effect. Yeah.
How is that offset by, I guess, that entropy, right, has to be paid off something, right? Is that still paid off by the water that's displaced?
Is the entropy paid off?
Yeah, because I mean, you're restricting entropy, right?
Yeah.
By
And you got the way you were able to do that is you were able to liberate the binding energy associated with this extra cabbage out here. Even though it's far away, it got liberated in such a way as to be used to reduce entropy, right? So it's very subtle, right? Like you're out here somewhere, you're taking this. What do you mean you're using it? You know, and I can't explain it better than I have. But the conventional way of talking about it is we use the binding energy to promote catalysis. Well, you know, that's still general. What about catalysis? Well, we use it to improve kcat. Okay, what is kcat? All right, it's chemistry. Well, how does it use to promote chemistry? Well, it immobilizes the cis bond with respect to the serine, 195. And now, once we've said that much, right, we've said about as much as 99% of enzymologists on the earth will want to hear, or will be able to digest or understand or care about. Right? Question over here somewhere? Okay, so that's the use of binding energy in catalysis. Yeah.
Does the extended then that's added on to substrate BNC also lend any like electron density to the chemistry happening in active site to help like stabilize transition states?
No, there's nothing changed because it's too far away. Okay, another chymotrypsin example. Here's a chymotrypsin substrate that does not look like a peptide. Instead, it's an ester. A peptide bond is an amide, which is more stable than an ester. So the enzyme has to really bring to bear a lot of catalytic emphasis to cleave an amide or a peptide. Right? There's more resonance there. The bond is stronger. Here, to cleave the ester, it's not so tough, but it still does it. And we use these ester substrates, in this case, paranitrophenyl acetate, as tools to study the enzyme. You measure the ester, you measure the amide, you compare them, you think about it, make mutants, etc. Right? So that's why it's not a peptide, it's an ester. So the ester is cleaved to give paranitrophenol, which can be detected. Right? Here's on the y-axis is the product detection. Right? But that's only generating the acyl enzyme. One product is formed. Remember, one product is formed in the first half of the reaction. The acyl enzyme forms. Water has to come in to resolve that, right? So here's the water in the second step. Okay. So this slide is intended to say something about which of those steps is faster than which other one. Okay. So it turns out that this is the fast step, the first one, and here's the data. So the product that's building up that you're actually detecting is not the final product in the reaction, it's the intermediate product, right? And the way this experiment is set up is that there's more substrate than enzyme, but notice that I put 1 greater than and not 2. Like it's greater, but it's not a huge amount greater. Like maybe it's 10 times greater or 5 times greater. And how much you have to do depends on how sensitive your signal is. But if you have a lot of substrate, if you don't have much more substrate than enzyme, then a lot of the enzyme is working right away. And that means a lot of product is formed right away as compared to, say, if it was 100 to 1 or something, right? So you're detecting more product, so you can see the signal, right? What you see here, you would see every time there's a fast step followed by a slow step in a mechanism where you're detecting that first product, right? But you might not see it experimentally if it was only 1/100th of the total product. This little thing here would be a tiny little thing, and you'd be like, that's error in my data. I won't even look at it. But if you set up the experiment right, you could actually see this thing be fast, right? Now, if this step were slow, and this step were fast, right, then this formation would be slow. In fact, it would limit the overall rate. So then you just have a straight line, because this straight line part is the steady state rate after the first turnover. So this is an example of a pre-steady state experiment where we observe the first turnover, and then we also observe the steady state. Up until now, everything we've seen is, oh, we're just looking at the steady state every time, right? Now we're just taking for one measurement, right? This is a time course. We see this is what we call a burst of product, right? That indicates that a late step is rate limiting. Questions?
We had the other example that was kind of analogous to chymotrypsin that had water first.
HIV protease.
HIV protease, so that would be linear. Or was it- Well, assuming the
Well,
water
no,
is
it
the
would
slowest.
depend on the details for that particular case, but in that enzyme, there's no covalent intermediate. So it would be tougher to set it up. You have to think about how to, here it's more straightforward because you can liberate a spectroscopically active product after a part of the reaction that also forms a stable intermediate. Right? So it's favorable for this kind of experiment. Right? But it doesn't necessarily have to do with water or not water. Right? Water attacks can be very fast in some enzymes, super fast. It just happens that in this case, for probably some structural reason in the active site, the water attack is slow. Yeah.
So I'm just curious, is the derivative that produces a faster and a slower step if you did now, would you just measure the acetic acid product as being formed compared to the phenol and see how they change?
You could measure them both and compare them if you had a way, if you had a signal to measure the acetate product. Not so easy. You'd probably have to collect the tubes and run a mass spec or something, HPLC. Yeah. This kind of assay is great because it's an example of a continuous assay. You put your enzyme and substrate inside the spec, right? Close the top, you know, and hit go on the computer, and your data accumulates in the machine, and you see it. You're done. You don't have to like extract, run gels, God, right? You don't have to do any of that stuff. Other questions? So these are two subtle points about enzyme catalysis, or we could call much more advanced points. Right? The use of binding energy catalysis and the idea of the pre-steady state versus the steady state and the determination of the rate limiting step. Okay, now we can replot kinetics. We can replot V equals V max S divided by Km plus S as a linear equation by playing around with the algebra. Play around with the algebra enough, and you will find that you can get to here. I don't recommend that you take the time to do it, but this replot can be useful in analyzing data. Right? So there's no new concept here about how the enzyme works. It's simply taking the data, the V versus S data that we talked about, and replotting it as 1 over V versus 1 over S. And shortly, I'll show you where an application in inhibition where this kind of plot gets used more often. So it's worth knowing about. It's worth knowing that enzymologists do this kind of thing. There's other ways to replot linearly. This is called a Lining-Verberg plot. There's something else called an Edie-Hofstee plot. There's just different ways. This is just data analysis now. Okay, so this is y equals mx plus b. yx, m, the slope, Km over V max, right? B, 1 over V max. Linear equation. Not very intuitive about thinking about reciprocals, right? V versus S is much more intuitive. You see the saturation, you get Km out of it. You know, this is like, you know, I get Km over V max from the slope. What is that, right? Nonetheless, it's useful because sometimes you like to look at straight lines instead of curves. Okay? So that's it about Lining-Verberg. Some enzymes bind multiple substrates, and when they do, they might bind those substrates in an obligate order. Like there's A and B, and you must bind A first. If B does not bind, except to the enzyme A complex. Right? So here's random order. Many enzymes are random, and enzymes doesn't care. It'll bind S1 or S2, right? And products form later. Or if it's ordered, it has to bind S1, then S2 binds. What do you predict about what S1 does to E in this case?
Be a